So can you see my screen?
Yes, that's excellent, and we hear you fine too.
Great.
So please feel free to start at any time, and I'll give you a 2-minute warning at the 10-minute mark.
Okay, let me start. Thanks, IB. Hello, I'm Yoon, based at the University of Sydney. So today I'll be presenting on the ASKAP FLASH project on behalf of the FLASH Survey Science team. So FLASH is the first large absorption survey in H1, searching for H1 spectral lines from the intermediate redshift range out to 1. So now survey is at the final stage of pilot survey 1. And actually the main focus of the team at the moment is on data processing and validation process. But we get very excited in science aspect as well whenever we detect absorption lines from the random direction of the sky. So today this talk will be a bit general. I will overview the current status of the survey with the first result we could see very recently. So FLASH is a collaborative work done by huge efforts from many people in the team. So the team is led by 2 PIs, Elaine Sadler and James Allison. And here you can see the photo of the core group members of FLASH, mostly based in Sydney now. But the entire FLASH collaboration consists of a large number of people from many international institutions. So as I briefly mentioned in the beginning, FLASH is a wide field untargeted H1 absorption line survey using background radio continuum sources with ASKAP. So it is an untargeted survey. So basically we don't know where the absorption line pops up. So whenever we detect an absorption line, the next step of us is to collect the information from the line itself and all the archival multi-wavelength data as much as possible to trace the origin of this line. So FLASH is one of the 10 ASKAP survey science projects, and it is the very first study of H1 content of individual galaxies in the intermediate redshift range, which has not been studied well previously. So it's toward the whole southern sky. So the ultimate goal of the surveys are summarized here. So we aim to trace the evolution of the cold gas in galaxies. So what we do is observing the entire southern sky and extract the spectra toward radio sources in the low frequency band with ASKAP. So it doesn't target individual sources. Instead, we observe some selected fields and detect any absorption line from there in the redshift range from 0.4 to 1. So we will eventually cover about 34,000 square degree of the sky. So considering the expected number as a function of the observed frequency, we expect to see roughly about 1,000 H1 observers from the sky area. So let's talk more about H1 absorption line. There are several very nice talks introducing H1 absorption science during this meeting by Emily Tristan, James Dempsey, and more people. And H1 lines, both emission and absorption, come from the spin of neutron hydrogen atoms and gives good information of interstellar gas. The H1 emission gives good global property of galaxies. And I'm sure Tristan will show fantastic talk about H1 emission study after this talk. But the emission line is very weak to be detected at higher redshift. So with the large telescope to date, we can only detect H1 emission out to redshift 0.4, and it still requires a huge amount of observing time. So there is a strength of H1 absorption observation in this aspect. So if we observe H1 absorption line, the sensitivity is independent of redshift, and the detection limit is determined only by flux density of line of sight background sources. So on your right-hand side, there are 2 types of absorptions we will expect to observe in this survey. So one is intervening absorption line due to the background radio sources, and the gas is located in between radio source and us. So it allows us to study the number density of 21 centimeter observers as a function of the cosmic evolution. And another one is associated absorption line, which is directly related to the host galaxies and AGM. So these are good targets to understand the key physical processes inside the system. So in the middle panel shows H1 content as a function of the redshift, and flash will contribute this redshift range in the red box, roughly 4 to 8 giga lookback time. So ASKAP is a great telescope to achieve the goal of flash. So the pilot survey 1 we have been working on is based on the observation using all 36 completed antenna for the first time. So the key advantage of ASKAP in flash aspect are, first, it's been built in radio quiet site, and it has a long 300 megahertz bandwidth and no significant RFI in this frequency range. And it has a wide field of view, which is 36 square degree in a single point. So we have already completed successful early science with targeted quasars before starting the pilot survey. So on your right, you can see some examples. So there are intervening absorption line cases from the bright background sources. So especially the middle one from the gamma 23 field studied by James and the team. The absorption line was found from the gas of the foreground galaxies at the redshift of 0.36, but the line origin is background radio sources. So like other ASKAP surveys, FLASH is undergoing pilot survey to prepare for the full survey, and the pilot survey observation have completed early this year for FLASH. So it covers about 1,500 square degree observed for 100 hours. And the aims of the pilot survey, one is to test and validate observation and data processing strategy for the full survey. Specifically, we will measure the detection rates for associated and intervening observers using the largest database. And another thing is this very crucial step to validate our observation strategy and data processing pipeline before going to the full survey. So the plot on the right shows the field we choose. So it looks like the fields are quite randomly distributed, but these fields are chosen because there are much available multi-wavelength data based on gamma, sloan, darkness survey, etc. So this is very useful, especially to confirm if our absorption features are real or not using the multi-wavelength data. And again, the frequency range is from 700 to 1,000 megahertz, correspond to redshift from 0.4 to 1. So for the pilot field, this field scale, the field scale shows processed field. And we finished our pilot observation only this year, and the data pipeline test and quality data validation are underway. Now we found some detections from the cubes. So this is a very brief summary of data validation process that we have to do when new data comes. I'm not gonna go deeper, but this is one of the very crucial goals of the pilot survey. So for example, we first had a quick look at the continuum data and to check if there is any missing beams or the validity of the spatial distribution, and the flux is not that different from the other survey. And another thing is, compared to continuum data, for flash, the spectral lines are more important for flash science. So we measure the noise in different ways. So the plot in the middle shows the noise measurement across the full band. So flash covers quite a large band, so many things should be divided into small chunks of the band. What I would like to highlight here is that the RMS noise level is uniform across the entire spectral band and in the continuum images, and with different RA deck and observation time, like daytime or nighttime observations across the different targeted fields. So now finally, let's move to the latest preliminary results of the survey. So these are some new detections we found from the pilot survey observation. So as flashes on targeted surveys, so these lines are from the random sky. So the expected RMS is a few millijansky level per channel. And especially these samples have been double-checked with online finding tools called Flash Finder run by James Allison. So, so far, most are confirmed as real lines, and they are likely to be related to luminous red galaxies directly or indirectly. So here is a more deep look at one of the example of strong intervening observer candidates. So in the middle, you can see the first spectra. Yes, thank you. We can get from the cube and the clear baseline across the long band. So the great thing here is we can get this large spectra at once. And there are some artifacts, but no significant RFI and very stable baseline. So you can see clear detection on your right-hand side. MVSS source at a redshift 0.4, and it has relatively high peak optical depth, which is about 0.38. And unfortunately, it is located behind the foreground star, but deep imaging with DACAM reveals it can be related to a red object, which is off-centered from the radio source sightline. So the next one is PKS source, which is one of the associated observer candidates we found. So unlike the previous one, it has optical counterpart. So the optical image shows a faint candidate for the 0.581 redshift observing galaxy. And the line is unusually broad for these kind of H1 observers, so suggesting that it could either arise from cold gas in the host galaxies of radio source, or multiple sight line exists due to strong lensing effect, but further data for discussion is required. So in addition to the spectra, another great thing is we can get high quality wide field continuum images at the same time. So the image here is to show some of the continuum images we could get from the pilot survey observation. And most continuum images generally look great, and the RMS is roughly 100 microjansky level. So these shown here are enlarged images for some radio sources. So the main goal of the flash is on spectral, but our high quality continuum images are enough to find the interesting radio sources. So we found that there are a number of radio sources showing intriguing morphology. So it allows us to extend our work to morphological classification or comparison with other radio imaging, including REGs, FIRST, or MVSs. So we expect this is a good synergy with other multi-wavelength imaging. The good thing is flash covers some sky area which haven't been reached by previous Earth sky survey like MVSs or FIRST before. So we expect to get more unique data as we proceed the survey. So here's just to briefly summarize. I think I should stop here. Thank you.
Thank you very much, Hyein. We have one talk on Slack from Leonard Balkenhol. Thanks for the great talk. Sorry if I missed it, but what is the beam size and shape of ASKAP?
So maybe you can just see this mosaic image. So the beam resolution is 20 arcsecond, and its beams covers roughly 6 by 6 square degrees.
Excellent. And since I cannot see another, oh, Ron's got a question. If your background source is resolved, you can match the H1 absorption. Is that useful?
Yeah, I think that is a very crucial point. Yeah, I think this is very very useful if we just can separate the velocity information from the resolved part to interpret the origin of the line. I think that is a very important point.
Cool. And since I can't see another question, I will ask one of my own. So is flash detecting as many absorptions as they expected from the early observations?
So far, the detection rate is not that higher than we expected, but we still process the data. So I think we should wait for the final conclusion.
Thank you very much, Hyein. That was an excellent talk and beautiful data. Any questions on Zoom LAN or in the hub? No, if not, let's give Hyein a round of applause again. We next have Tristan Reynolds from UWA. Tristan, I'll give you a 10-minute warning as usual. And, if you could just exit full screen. Yep. And then it's Acrobat. Yep. There we go. And then view. Oops. Sorry. Oh, do you want to share screen, please? Yeah. Everyone in Zoom land seeing this? Full screen one. Okay. All right. No complaints. Please start.
Great, thank you. So hi, I'm Tristan, and I'll be telling you today about Wallaby observations of the Hydra 1 cluster. So this is looking at the Hydra 1 in neutral hydrogen. So as Hyein's already told you a bit about neutral hydrogen, or H1 for short, just a few additional points is that in neutral hydrogen, we get a wealth of information. We can get the distance to objects. We can measure their motion, their rotation, their mass, their surface density, and other things that make H1 important and why you should care even if you're not a radio astronomer is it's important for the conversion of, for star formation via the conversion to molecular hydrogen. And it's also a very sensitive probe of the environment and the effect of the environment on galaxies, as I show here in this very nice image of the M81 group, where you see in red the H1 connecting the various galaxies shown in white and pink colors. So Wallaby is another one of the surveys on ASKAP, and it's the all-sky H1 survey. So while FLASH looks at H1 in absorption, Wallaby looks at H1 in emission. And it's going to observe over 75% of the sky, detect roughly 500,000 gas-rich galaxies out to only low redshifts, 0.26. And it's going to spatially resolve several thousand of these galaxies. And this is going to be rather transformational in our understanding of H1, because up to this point, there's only been spatially resolved H1 observations of roughly 500 galaxies. So we're going to increase this by roughly an order of magnitude. And this is also on ASKAP. And just to kind of give a sense of the field of view of ASKAP, in the lower panel here, I'm showing the footprint of ASKAP on the sky compared to the Southern Cross. So if you look in the night sky and look at the Southern Cross, that's how large a region of sky ASKAP sees at one time. And you can also see in relation to the full moon in that image as well. So Wallaby is also currently going through its pilot survey. Within that, currently there have been 3 60-square-degree fields observed. In this talk, I'm just going to focus on the Hydra field shown here, which, based on its name, includes the Hydra cluster in the left-hand side of the observed region. So these observations, a total of 60 square degrees on the sky. Total integration time was 32 hours to observe all of this. The spatial resolution of Wallaby is 30 arc seconds. Spectral resolution, 4 kilometers per second, and a sensitivity of 1.6 millijanskeys per beam. So here is if we take that entire observed region and initially just do source finding over all velocities out to 22,000 kilometers per second, then we detect roughly 270 sources as shown here. So basically every point of color in this image is a H1 detection. And as I mentioned just before there were roughly 500 galaxies spatially resolved. Within this single field, we're detecting nearly half of that number. I will note not every single one of these galaxies is actually spatially resolved. Some of these are point sources, but we're getting close within a single pilot survey field of roughly half of what exists in the literature to this point in time. Now I'm focusing just on the Hydra cluster, which is at roughly 3,780 kilometers per second, or 61 megaparsecs away from us. So here I'm just showing galaxies in the low redshift portion of that previous image. So just galaxies below 7,000 kilometers per second. So in this image, there's roughly 150 H1 detections. And here I'm showing the center and viral radius of the Hydra cluster in the star and dashed circle, and showing that within this field of view, we are able to probe out to roughly 5 viral radii away from the cluster center, which gives us an excellent opportunity to compare the cluster to a reference field population within the same set of observations. So everything's uniform between how these are all observed. Now, what I've now done is split up this sample into galaxies I classify as cluster members. So they're in blue in this and all future plots, in falling galaxies in pink, and field galaxies in orange. And here I've used the phase-space diagram. So it plots the velocity of each galaxy relative to the cluster on the y-axis against the projected distance of each cluster from the cluster center on the x-axis. And because Wallaby only detects galaxies in H1, there are lots of galaxies Wallaby won't detect. And so galaxies which are not detected in H1, I use light shaded colors for, and they're galaxies which are in the 60F galaxy survey, but do not have a Wallaby counterpart. And there's roughly 150 galaxies in this field. That's by coincidence. There's no selection to go and have equal numbers of H1 detections and non-detections. And this is just showing both galaxies detected in H1 and not detected in H1 out in the sky, so just in projection. And you can see that now the cluster region indicated by the dashed black circle has a much more clustering, because that's where most of the non-detected galaxies reside. So moving into some of the properties of the galaxies Wallaby detects, here I'm showing the gas fraction stellar mass plane, where the galaxies detected in H1 are the dark open symbols. Galaxies not detected in H1, I have upper limits for, based on the distance to the Hydra cluster of 61 megaparsecs as downward arrows. And then as a reference for comparison, the XGAS sample. So a sample of stellar mass selected targeted observations as the gray points in the background. And I'll note that XGAS only, like what their sample selection was galaxies between a stellar mass of 10 to the 9 to 10 to the 11.5. So Wallaby goes and also is able to go and probe down to just being a blind survey, much lower stellar masses, and roughly half the detected sample is below the XGAS limit. So with Wallaby in the future, we'll be able to go and really probe those lower masses. And then here showing the star formation rate versus stellar mass with the star forming main sequence as the dashed line. All the galaxies Wallaby is detecting lie on and around the main sequence. And so from this plot and the previous one, the takeaway message is that Wallaby is detecting gas-rich galaxies and galaxies which are star forming, which isn't unexpected. Wallaby is a blind survey, so those are the galaxies that you would tend to observe. But it's nice to go and actually characterize that. So now moving on to actually doing some comparison between those galaxies we detect in the cluster sample and those galaxies we detect in the field sample, and also the infalling region in between. I've looked at the ratio between the H1 diameter of the galaxy, which we can measure because these galaxies are spatially resolved, and the stellar disk diameter measured in the R band from pan-stars, with just one galaxy shown, for example, on the left. And here I'm going and showing the histogram distribution of those cluster, infalling, and field galaxies with the medians above the distributions for H1 detections as the solid symbols. And then if the median, if we include those H1 non-detected galaxies, so those galaxies for which we can measure an upper limit in the H1 size as the crosses. And we see, although there's no massive decrease in the H1 detected galaxies to massively truncated radii, as we do see in other more nearby clusters. Thank you. We do see a clear trend of galaxies in the cluster have smaller, on average, size ratios compared to in the field, which is a sign that gas is being removed from the outer disk. And then looking to see if this has any correlation to a reduction in star formation. Here showing the distribution of galaxies similar to the previous plot, but as a distance from the star forming main sequence. And for H1 detected galaxies, there's no trend. So this is just saying that, as I showed a few slides ago, that Wallaby is detecting star-forming galaxies, and as a result, the gas is just being removed from the outskirts of the galaxy and is not yet affecting the star-forming inner disk. So just some conclusions. Wallaby is fantastic for enabling direct comparison between different environments using uniform observations. We find in these observations that the cluster is affecting the gas properties. So it's likely environmental effects, removing gas from the outskirts, but not affecting the inner star forming disk. And at the distance of the Hydra cluster, Wallaby is not detecting significantly truncated disks or galaxies that are in the process of quenching. And I will just leave you with a nice image of all our current pilot survey data showing all the galaxies we've detected, which is on the order of the number of galaxies that are previous to this. We had spatially resolved H1 observations before this point. Thank you.
Thank you very much, Tristan. We now have one question on Slack from Mike Creel. Maybe a silly question, but what causes the empty region of no galaxies between a velocity of 2 and 4? I assume that refers to your phase space diagram.
Probably yes.
Do you remember that? We can quickly go back.
I think
So
that's meaning here. So I think it's simply a case that the Hydra cluster is well separated in velocity space, as there's not clear regions of infalling galaxies either in front or behind. Basically, those galaxies out at around 4, there's a few at roughly 1,000 kilometers per second and 2 galaxies at 6,000 kilometers per second.
Okay, second question from Anshu Gupta. Can you talk a bit more about why H1 and Wallaby galaxies in the center of the cluster are not significantly truncated?
So that is simply going to be a case of Wallaby's detection. So there are lots of galaxies within the cluster which are detected in H1. And it's going to be a case that it's not that those galaxies don't have H1, it's just that the H1 in those galaxies is below our detection limit.
All right, final question from Ron Akers. Any H1 with no visible galaxies?
Not in this, not in the sample I've looked at here, but in other pilot and early science data that there are. So keep an eye out for those papers coming out soon.
Thank you very much, Tristan. Do we have any questions in Zoom land? If not, John, feel free to share your screen. We have John Dickey now.
There you go. Can you see my screen?
We can see your Slack.
Oh, you still see my Slack. Yes, here we go. There, can you see that?
Yes.
Okay, very good. Let me start off by acknowledging the Mohanina people, the traditional owners and protectors of this land in Tasmania, where the university is and where I live also. So on Wednesday morning, Katie Jameson and James Dempsey showed some of the spectacular results, primarily the results for the small magellanic cloud that we have from GASKAP. I'm going to talk a little bit about the galactic side, that's the G340 field. The background science question is this: I'm going to talk primarily about absorption, which traces the cool neutral medium. And the cool neutral medium is really very distinct from the warm neutral medium. In the Milky Way, the warm neutral medium dominates the 21 centimeter emission. And to see the cool neutral medium, you have to get rid of the 21 centimeter emission and concentrate just on the absorption. And I'm going to look just at absorption towards continuum background sources. And the real deep question that I'm after here is, does the mixture of cool neutral medium and warm neutral medium change across the galaxy, and particularly in the very outer part of the stellar disk? That's important not only for galactic structure and interstellar medium physics questions, but also to understand absorption like what we saw in FLASH in other galaxies, to understand what the spin temperature, that is the excitation temperature of the 21 centimeter line should be. So I'll talk just for a moment about the field, and then I'll go on and talk a little about the inner galaxy and then about the outer galaxy. Now, if you had radio eyes and looked at the Milky Way, you'd see something like this. This is about the size of your thumb at arm's length. This is not from GASKAP or from the ASKAP telescope. This is from the Southern Galactic Plane Survey 20 years ago. With GASKAP, we squint our radio eyes, and that same field looks like this. Let me just bounce back and forth. I don't know if it's obvious that this is even the same field. The reason we do that is that we have to filter out the 21 centimeter emission in order to see the absorption. The 21 centimeter emission is very bright in the Milky Way, and it's heavily modulated by the interstellar turbulence, so that it has structure right down almost to 1 arc minute in scale. And that would completely overwhelm the absorption towards all but the strongest sources if we didn't filter it away. So here we put a high pass filter of about 1.5 K lambda. So that we're really, and our beam size here, by the way, is about 7 arc seconds. We're mostly absorbing, filtering away all the emission, even in the continuum emission, but certainly in the line emission. And that's what we have to do, and that's what we want to do. Unfortunately, ASKAP is a very good telescope for doing that because it has a lot of baselines at just the right length. Now, the area that I just showed, that rectangle, is small compared to the footprint of the PAF field on the sky. Here's longitude across the bottom. Let's see if I can get this. Yeah, longitude across the bottom, latitude going up and down. We're going from about 336 to about 345 in longitude. And this is, oh yeah, before I leave that slide, let me say it's very important to separate the extragalactic and the galactic continuum sources. And you do that by doing a whole lot of astro queries to the Vizier database, where they have many survey results, tables of sources found in different ways. The Atlas Gal and the WISE H2 region catalogs contain most of the galactic sources as far as we know. So in the end, we have about 100 galactic sources and almost 250 extragalactic, of which about 200 are strong enough that they're pretty useful for absorption. Now I could show a lot of spectra, but here are just a few. This is, well, everything on this slide is just showing that the quality of the spectra is very good, both in terms of their bandpass calibration and also in terms of the sensitivity. Here's another plot of the quality. Now I'm stacking the spectra, averaging weighted by the noise, or 1/2 square of the noise. You can see there's a little bit of roll off up here in the baseline beyond 200 kilometers a second. But pretty much for the velocity range I'm interested in, the baseline is very good, and the calibration of the spectra is very good. Now, just to remind you, at longitude 340 or minus 20 degrees, the inner galaxy gives us negative velocities, the outer galaxy gives us positive velocities. We're going to take a walk down this line of sight from the sun, and the first thing that we'll note is the subcentral point, or the terminal velocity point, the tangent point, where we get the maximum negative velocity. If you superpose where we think the spiral arms are, well, our line of sight in this case crosses all the spiral arms. In fact, it crosses almost all of them twice. Either mostly in the inner galaxy, but then again in the outer galaxy. Notice also that this tangent point is smack in the middle of the near side of the 3 kiloparsec arm, which is actually expanding away from the galactic center, but that doesn't mess us up because there the expansion velocity is perpendicular to the line of sight. We will then go on and come very close to the far end of the bar, where there's a great deal of star formation, and we'll see many of the continuum sources, in the galactic continuum sources, are in that area. Then we'll come on out through the Scutum-Centaurus arm. This is at about plus 10 kilometers a second. And although this isn't labeled, this is the Carina arm at about plus 20, 25 kilometers a second. This actually shows all of that better, but I won't take the time to talk you through all of that. So first, let's take a look right at the subcentral point. This is explaining a little bit how we have to shift the velocities of the different spectra before we co-add them or before we stack them. This is not from stacked spectra. Each of these blue dots in this panel is a separate background source, and I'm averaging over velocity ranges, minus 145 to minus 125, that straddles the terminal velocity. Stepping back from the terminal velocity, 125 to minus 100 to minus 75. So this is sort of smack in the middle of the 3 kiloparsec arm. This is stepping back a bit on either side, so we're getting to the end of the bar and stepping back a little bit further. You can see that this is latitude, of course, across the bottom. The absorption, the CNM, is pretty well fit by Gaussians in Z. But the widths of those Gaussians are much narrower than they are at the solar circle. Right at the extreme tension point, we get about 50 parsecs for the sigma of the Gaussian, or the scale height, about 78, and then down to about 61. Here at the solar circle, well, in the solar neighborhood, we would be seeing about 150 for that. Over here, these purple dots are the galactic sources. Of course, many of them show no absorption at all at the tangent point because they're closer by than that. Many of them show much more absorption than the extragalactic sources because they are, in fact, star formation regions buried in the CNM associated with the molecular clouds there. Here I do some fitting to try to determine the mixture of warm and cool phase in the 3 kiloparsec arm near the terminal velocity. The most important number on here is simply that my determination of the temperature of the cool neutral medium, not the spin temperature, but the actual physical temperature of the cool neutral medium there. It's pretty cold, about 45 degrees K. We can talk about that if there's questions. Now let's go on to the outer disk and let's take a look across the far, far side of the outer disk all the way until we get to the place where the circumgalactic medium begins. And so now we have to scale down that picture. We're going well beyond the stellar disk. This is 1 times the solar circle radius, 2, so this is about 16 kiloparsecs, 3, 4, so now we're at about 32 or 33 kiloparsec radius. Here's the surface density of H1. This is done from the lab survey data by Ku et al. But you see that by the time you get out to about 12 kiloparsecs, that's a bit beyond the solar circle, it starts to drop off. The surface density of H1 starts to drop off fairly exponentially, but with a fairly long exponential scale length. This sharp edge here in the first quadrant is because of the warp. And part of the reason we choose 340-degree longitude for our test field in the Pilot 1 survey is because the gas doesn't warp very much there. We can see the warp, we see it go up and down a bit, but it goes all the way out in our field. We have to rescale the velocities before we stack them, and we'll do a lot of stacking. Here's some stacking, comparing the galactic sources with the extragalactic sources. And from now on, I will concentrate on this little box here that is positive velocities, but blowing up the scale so that you can see these smaller features that you see way out in the outer galaxy. Now, there are enough sources here that we can divide the field into 6 different areas, and I won't go through all of that, but each area shows different features. And in fact, for example, here, we're looking at the Carina arm at the negative latitudes. It's very deep, but over here at positive latitudes, not at all. This is the small warp that we see. A degree or so of warping is common at this longitude. Now, we actually have enough sources that we can break the sample into 2. So we can do sort of a jackknife test to test the robustness of the results that we're seeing here. So these blue and red squiggly lines are 2 different samples, completely disjoint samples of background sources, where we're averaging the 2 samples and then comparing. And you see that sometimes the comparison is not that good, but sometimes it is quite good. And for these important lines, really out far across the outer galaxy. We're getting quite good agreement, and I have very strong trust in these results. This is, of course, velocity at the bottom, but the corresponding galactic radius going out here, so 2, 3, 4, 5 times the solar circle radius. So here we're all the way out to about 40 kiloparsecs, here about 32. And we're still seeing CNM, we're still seeing absorption, and we're also seeing emission, of course. What we're looking at here is, again, for 2 separate disjoint samples, the galactocentric radius at the top, the LSR velocity at the bottom. The red is the emission, and I take the emission from the Hi4Pi survey, which is Park's data, and the absorption is the green dots. The scatter in the samples is about 50 sources in each sample, and then the standard error of the mean. The two, one side and the other, are really just the same result, but taken with a different sample of 50 sources. I can blink them back and forth, and you see that there is actually quite a bit of shift in the outer Scutum Centaurus arm and in the Carina arm. And you can see also there's a lot more gas there. But as we get beyond that, things settle down. And although there is some change between the samples, they're pretty consistent with each other. Now, I can then go on and take the ratio. You see the ratio of these doesn't change very much between the warm and the cool. And that's what the spin temperature is. It's the emission divided by the absorption, 1 minus e to the minus tau. The 2 samples are the different colors. And again, we're going out to about 40 kiloparsec radius, and then the gas starts to get warmer. The differences among these points are important and they're interesting, but I think we need a little bit more signal to noise, and we need a larger sample before we can say certainly that there are big changes in the spin temperature in the outer disk from one place to another, and to understand those. Here, what we take, here I just show that almost all the points are within the region 250 to 400 K spin temperature. So I think it's safe to say that in the Milky Way outer disk, the spin temperature is mostly about 300 K, plus or minus maybe 50 or 100 K from that. Just the physics that we're talking about here is interesting. Okay, the conditions way out at the outer boundary of the disk, or the beginning of the circumgalactic medium, well, some of these we know better than others. The density of H1, not necessarily the total density, because much of the gas could be ionized there, but the density of the H1 is very low, 10 to the minus 4 per cubic centimeter. The gas phase abundance, well, this is the oxygen abundance, quite small compared to the solar circle, not super small. It's not like a dwarf galaxy with no star formation or something, but it's pretty small. The cosmic ionizing background is probably quite important, and in my opinion, could be both heating and cooling, or determining, let's say, the spin temperature through the Washausen field effect. And there's probably a cold flow accretion, which is streaming in through that boundary between the circumgalactic medium and the edge of the disk. So there's a lot of physics to do in this environment. So finally, my conclusions: in the outer galaxy, T-spin's about 300 K, between about 15 and 40 kiloparsec radius. The CNM is in clouds at velocities that more or less correspond to the spiral arms that we see in a large scale in emission. In the inner galaxy, the CNM scale height roughly corresponds to the molecular cloud scale height when we're in at about 3 kiloparsec radius from the center. So just to finish, GASKAP has made good use of pilot phase 1, but we need a lot more. What we asked for was 50-hour integrations along the plane, not 16 hours like what we have here, and many more fields. 55 fields will get us all the way around the galactic plane from plus 40 degrees declination all the way around to plus 40. So with that, we could do really a great deal. So I'll leave it there, and thank you very much.
Thank you very much, John. Can you unshare the screen? And then there's one question from George Heel.
Yes.
I may have missed this part of what you said, but is the radial variation in sigma z compatible with what you'd expect from the gravitational field and or indicating flare in the H1 disk?
Yeah, hang on just a sec. I'm trying to unshare my screen here.
Sorry.
Stop share. Okay, good. Now, yeah, what was that question again? What is the reason for the cold gas at such heights? Is it formed there or taken through outflows or winds? Is that the one? Or George Hill, I'm sorry. I may have mismarked, but is the radial variation in sigma z compatible with what you'd expect from it? Yes, very, very important question. As we go out across the disk of the Milky Way, the gravitational potential due to the stars flattens. And as it flattens, the scale height should increase, and it does increase. We can see that in the emission. For the absorption, I would say, yeah, this is pretty much consistent with what we would expect. Now, in the bar, it's a little funny in that there is this ultra narrow stellar component, which has a scale height of about 50 or even a little less parsecs. And I think what's really going on here is that the molecular clouds are relaxing in the gravitational potential, and the H1, the cool neutral medium, is mostly all associated with molecular clouds in the molecular ring and at 3 kiloparsec radius.
Thanks, John. I think there are more questions from Amit Sita in the Slack, so it would be great if you could answer it there. But thank you again, and we now have Nithya.
Thanks, Ivy. My name is Nithya. I recently joined CSIRO as a research scientist. I'm going to be based in Perth. This is my first ASA meeting, so it's great to see you all. I'd like to start out by acknowledging the traditional owners of the land, sea and waters here in Australia, and pay my respects to their elders past and present. Today I'll talk to you a little bit about the prospects of detecting 21 centimeter neutral hydrogen structures in the IGM on cosmological scale during the cosmic ionization epochs, using an independent approach, namely 21 centimeter absorption against bright radio background objects. Not necessarily bright, but using a statistical approach that I believe significantly improves the prospects of its detection. So shown here on the top is a simulated picture of the ionization history of the universe, where it goes from being completely cold, dark, and neutral in the very early times to having the first stars and galaxies and quasars form, which radiate photons back into the universe, starting to ionize the medium around them, and eventually you'll get a completely ionized universe as it is today. So it represents an important phase transition, astrophysical phase transition in the universe, going from a completely neutral universe to a completely ionized one. So there's a couple of standard approaches at radio frequencies to detect this phenomena. One is the global signal experiment, which is essentially looking at a sky averaged spectral feature, either an emission or absorption, as it's shown here, done by single antenna experiments such as EDGES, SARAS, REACH, MIST, Hyperion, and many others which I probably have left out. I'm sorry about that. The alternate approach is to look at the fluctuations on different scales as seen here. And that is done using interferometers. Such as MWA, HERA, LOFAR, and also the upcoming SKA1 low. Note that all these ones assume that the CMB acts as the background radiation.
Yep, just go share it. And as you were.
Sorry?
And then press was great.
Thanks. So the independent approach to these earlier approaches is to look for 21 centimeter absorption against background objects. And this was proposed almost 20 years ago. It's very similar to the idea of Lyman alpha forest. When you look at a quasar spectrum, you got these intervening clouds and they absorb the Lyman alpha radiation. So same thing happens when you look at radio frequencies. There's the synchrotron background radiation from which the hydrogen clouds absorb the 21 centimeter portions of it. It turns out that if you work out the radiative transfer equation, the absorption profile that you see, especially when your background source is very bright, you see that the absorption profile is proportional to the strength of the background times the optical depth. So the stronger the background, the more amplified the absorption is and the easier it is to observe. So if you end up finding a very bright background source, you have a useful knob where you look for these spectral features. So what have been the prospects of direct detection? By direct detection, I mean like looking at these spectra and looking for these absorption features. So the fiducial parameter values that it depends are shown here. So first of all, you need tens to hundreds of millijansky background source. It's a very strong source at these redshifts. And you require a high optical depth, very sensitive instrument, and a long time to observe them, thousands of hours. There have been a couple of follow-ups, and it's actually so far not given anything concrete yet. So the downsides of this direct detection approach is one, firstly, the prospects of all these parameters optimistically lining up are very difficult. And second, even if you did, it's probably not going to be representative of the universe. It's probably an outlier in one particular direction. So the natural idea solution then would be to look at a statistical detection where you observe, do the same thing, but against a large number of lines of sight and get these spectra. But the important point here is that all these background objects are not needed to be bright. So they could still be faint, but the fact that you have a large number of lines of sight kind of compensates for the fact that they could be faint. And its modeling has shown that these sort of faint objects in the background can make a significant contribution to the reionization process. And it's also shown that there could be a significant number of them sitting in there. It's probably even in existing surveys. We just haven't identified them yet. So I've done a modeling combining three key ingredients of reionization, the background radiation, and the instrument parameters. Put these all together, and you can do the radiative transfer and come up with what the spectral feature is going to look like. Here's a semi-logarithmic scale with 0 point at the center. So the farther away from it is, the stronger the absorption is. So you can see that the thermal noise shown here in black, you can see a few features above the noise, but not all of them in the direct detection. So what we are going to do here is do a power spectrum of this line of sight absorption spectra, and basically take the Fourier transform and square it. And you can see that doing so, you are able to retrieve a lot more scales that were not possible even in the brightest case here. And then of course, this is for one particular line of sight. You could average the power spectra along hundreds to thousands of them and bring this noise down significantly. You can also turn the question around and ask what sort of instrument parameters I need for me to able to detect every single scale in this power spectrum. So you can calculate the sensitivity required for each different scale. And you can see that with SKA1, quite a few scales are already going to be accessible even for medium bright objects, and at higher redshifts, even fainter objects. Another way to also ask the question is, what is my PSF quality got to be if we want to detect the power spectrum? Because the point spread function that comes from unwanted objects in your field of view are going to be present in your line of sight, and they will have a spectral noise that confuses with the spectral signatures of H1 that you're looking for. So you can place constraints on the quality of your point spread function. And thirdly, you can also ask the question, how many sources do I need in order to be able to detect this power spectrum? And so you can see that you require of order, especially in the medium faint cases, you need of order 100 to 1,000 of them in order to see a lot of these different scales in power spectrum. So in summary, the 21 centimeter absorption is an independent method, and it's very important in key experiments like this. And the 1D line of sight power spectrum can improve the detection prospects significantly. It is robust to extreme sensitivity requirements. You don't need extreme sensitivity or very bright objects in the background. And it also is more representative of the universe. Technically, it might be actually simpler than doing a full 3D tomography as is being done. So even some of the current instruments, and definitely SK1 in the future, the prospects look pretty good for detecting this. Thanks.
So we have one question from Yuxiang in the Slack. Do you need a low redshift template to construct a non-absorbed spectrum?
Question. So the way I constructed my spectra here, or I took realizations of EOR simulations, and I just placed a quasar somewhere randomly at a high enough background. All I needed for the template is a synchrotron spectral index, and the rest of it is done by the realization of the cube that I got. So you can combine those two to produce a spectra. So it doesn't require detailed quasar physics to do this sort of thing.
Okay, second question from Ron Eakers. Do you get absorption against the CMB?
Yes, there is absorption always against the CMB, but in one of the plots I showed, in this plot, actually I didn't mention that the gray spectra here is if you only had the CMB. And these ones are for the specific background objects. So you can see that the contribution of the CMB is many orders of magnitude smaller than what the background object contributes.
Okay. Wow, the questions are coming in hard and fast. Okay, one from Natasha Hurley-Walker. Would you say that then the spectral smoothness is the most important attribute for arrays aiming to do this? Or does this come out in the wash somehow?
Yeah, the spectral smoothness is definitely important here again, and that's one of the reasons I also mentioned about the sidelobe response. But yes, that is one of the spectral smoothness systematics, but there could be others, and it's very important to get that right.
And we have a question from Elizabeth Marnie. Do you need spectroscopic redshifts for the background radio sources? How will this impact your ability to do this kind of study, i.e. difficulty in getting redshift selection effects this may introduce?
Yeah, you definitely need to target known locations of high redshift optics. So you need to know the redshifts beforehand. And optical selections has been a problem because the radio counterparts have been hard to find. You need them to be bright in radio, which is why the work that people like Nick Seymour and Jess Broderick and Guillaume are doing are very important. You need a radio identification, and the selection effects will be much more, they'll be better with the radio selection. Okay.
That's excellent. Let's thank Nithya again.
Thank you.
All right, we next have Yuxiang Chen.
Do you hear me?
Yep, we can hear you.
Okay, cool.
Would you like to share your screen?
Yeah, let me just share this now.
I'll be your looming voice at your 10-minute mark. So feel free to start whenever.
Can you see the slide? Yeah.
Yes.
Yeah, cool. All right. Good afternoon, everyone. My name is Yuxiang Chen. I'm a postdoctor at Uni Melbourne. So today I will be talking about Lambda alpha transformation in the intergalactic medium during the epoch of reionization. I should also say that this is different from what we were planning to talk about. So, but this is like an ongoing / almost finished project. So we would like to hear some feedback from you guys. So I hope you don't mind me changing the topic in the last minute. All right, so I will start with a review about Lambda alpha in terms of its constraining power to the epoch of reionization. I would highlight some observations that we focus during this talk. And that will present some of the results that we got from the Dragon simulation. If I still have time, I would end up with some future plans. All right, so reionization is a cosmic transition phase in our universe where the intergalactic neutral hydrogen get ionized. So here I'm showing you some Lycon slides of different fields, basically demonstrating this process. So in a Lycon, you basically get the redshift or the time dimension on the vertical axis, and you have the spectral variation on the horizontal axis. So basically, from high to lower redshift, the density contracts becomes more prominent, and in this high density peak, galaxy formed, and this galaxy would build a photon ionization UV background, and this UV background would one, heat up your gas, which can also suppress star formation in low mass galaxies, and two, ionize the intergalactic medium. And all of these quantities would determine the transmission of llama alpha in the intergalactic medium. So this is basically saying if you observe a high redshift star forming galaxy in a region which is high density or low UV background or low temperature or higher neutral fraction, it is less likely for you to observe its llama alpha emission, simply because the emission will be attenuated by the neutral hydrogen. All right, so, and this plot, I take it from Wong et al. 2020. This is basically a summary of the current llama alpha constraints on the neutral hydrogen fraction during UR. And so most of them come from high quality spectrals of high redshift quasars. If you focus on the llama alpha transmission, blues the line central, you could use the forest information to study the neutral hydrogen fraction. But this is mostly gives you constraints at the late stage of the UR. But we can also use the redwood information. This is to use the damping ring to study to study the neutral hydrogen fraction at early stage of UR. But this is not the focus of this talk. So as demonstrated by Mason et al. 2018, even the fraction of galaxies that present llama alpha can also infer the neutral hydrogen fraction. So basically, this is so at high redshift, we use color selections to select llama break galaxies. So you see nothing in the blue band, but you can see the galaxy in the infrared band. And then you follow up with spectroscopy, and then you can confirm the llama alpha emission. So if we take a look at the fraction of the llama break galaxies that actually shows their llama alpha emissions as a function of redshift. This is a plot I took from Laporte et al. 2021 early this year. And you can see the llama alpha emitter fractions increases from redshift 3 to redshift 6. This is usually explained by increasing star formation rate or increasing escape fraction. But going towards even a higher redshift, we see a dramatic decrease of the llama alpha emitter fraction. So this suggests increasingly neutral universe towards higher redshift. But like more recent study, when they focus at redshift 8 galaxies, but very bright galaxies, they also find that the llama alpha emitter fraction seems to be very high. But this is what only focusing on the brightest galaxies. So this plot from Robert Bassini et al. 2016. This shows you basically the number density as a function of the UV luminosity for all the llama break galaxies candidates at redshift 8. And highlighted in the colored region is the colored point histogram is the confirmed llama alpha emitters at this redshift. So you can see those are very bright galaxies among the current sample that we have. And we also have some preliminary results from Pascal O'Shea, where they follow up with a very deep Hubble image near these 3 llama alpha emitters. And then they find a larger number of bright galaxies just near in neighborhoods of these llama alpha emitters. So this seems to suggest that the Lambda alpha transmission in the AGM around those bright galaxies seems to be enhanced, either because themselves can contribute a lot of ionizing photons, or they are clustered together with other bright galaxies, so that the environments are ionized to a high degree. So, so we want to explore this. So this comes to this Dragons simulation. For those who stay in Australia for a very long time, you must have heard Dragons. So this is almost a 10 years project led by Stu White. So Dragons stands for Dark Age Reionization and Galaxy Observables for numerical simulation. I'm not talking detail about the simulations, but just to say we run our own embodied simulation and we built embodied halo merger tree. And upon the merger tree, we apply semi-analytic model where we can get the galaxy or even quasars observables quantity. So this plot basically shows you a stellar mass function from our model result showing in red, and it's consistent with observation showing in showing in gray, the redshift 0.6. This also shows you the importance of having AGM feedback in the galaxy formation model. And it also was to mention that we can also reproduce galaxy UV luminar function up to redshift 10, which is important to study the epoch of reionization. All right, so here are some results for this project. On the left side, I'm showing you the density field. On the right side is the neutral hydrogen field. And this is redshift 8. But in the stars, basically shows you all the bright galaxies that can be observed in, say, the Hubble deep field. And of course, larger stars means the galaxy is brighter. And on the right side panel, the stars only indicate those which can be observed in Lambda alpha, in Lambda alpha. So if you compare the stars on both sides, you can see that firstly, the bright galaxy follows the density peak, and they are located in large H2 bubbles. And to be transparent in Lambda alpha, those galaxies need to be either very bright, so like these very larger stars, or they need to be clustered so they can have collected larger number of photoionizing photons. Photoionizing budget. And to be more quantitative, this plot shows you the Lambda alpha transmission as a function of the H2 bubble size. And you can see there's a very tight correlation between the transmission and the bubble size. This is basically saying a larger bubble, if the galaxy sits in a large bubble, it is more likely to observe the Lambda alpha emission coming from them. And we also plotted against the local overdensity. And you can also see a positive correlation between the transmission and overdensity. And so if we draw a line on the transmission, basically this horizontal strap demonstrates where the optical depth becomes very high. And so we see that the transparent Lambda alpha emitters, which is above this line, has in general, on average, located in bubbles larger than at least 7 coulombic parsec at redshift 8, and they are also in overdense regions. We also split the sample by whether the galaxy is sitting with other galaxies in the same bubble. So for those with other galaxies, we call them satellites. So for those galaxies with satellites, it is showing in the solid field circles. And for those who don't have a satellite, this is the empty circle. So you can see that galaxies with a satellite seem to also have higher transmission. So this seems to suggest that if we can pre-select Lambda galaxies using their image and only follow up on those galaxies which has a neighbors nearby, it will have a higher chance for us to find their Lambda alpha emissions. Right, so if and this plot shows you again yes. So this plot shows you again the transmission as a function of the UV luminosity. So you can focus only on the bright side, which the red circle, which is the brightest galaxy in each bubble, And we see that brighter galaxies, because they have more outlining photons, they are located in larger bubbles, so they are in more transmissive AGM. And we also found that most galaxies brighter than 25.5 have a similar level of damping ring absorption, and they are all transparent in lambda alpha. So this again is echoing what we are seeing in the current observational sample. And we also did some mock image. Basically, we use the Hubble image. We have a field of view similar to the Hubble image, and then we count the number of galaxies within the field of view. And then in this small area here, I'm plotting the number of satellite galaxies that we found in the mock image as a function of the UV luminosity for all the bright galaxies. And once again, this was from, so this plot on the right shows you the preliminary results from the real images. So you see that we can find up to 6 neighboring bright galaxies near these transparent lambda alpha emitters. And this seems to be also consistent with the preliminary results from the observational campaign. All right, so I would very quickly mention what's the follow-up project. So with Pascal, we also have a JWST proposal that we will be following up on those Lyman break galaxies above redshift 6 to actually confirm their redshift with the grism from NearCam. And that, so because currently almost only 1% of redshift above 6 galaxies have a confirmed redshift. And so this means that the lambda alpha emitter fraction can be, well, not very accurate. And we also have many other JWST proposal. Well, actually, it's accepted. So they will be also observing more high redshift galaxies and also to find their lambda alpha emissions. And in the simulation point of view, we are working in the Genesis team. And so we have a PhD student, Balu, and he's working with the Genesis team, and we are trying to apply the simulation to this much larger unbody simulation. So we will get a much larger bright galaxy sample, which will give us more, which will allow us to do this study in a more statistic sense. And he has a post demonstrating some of his preliminary results. So if you haven't checked that, I recommend you to still to see his poster. And I will skip this slide and just finish with my conclusion slide. So I hope I have convinced you that lambda alpha is a physics-rich quantity and is observable, which in this talk I talk about the lambda alpha emitters can be used to probe the epoch of reionization. And using the Morexis semi-NM model, we found lambda alpha emitters during the epoch of reionization sit in bubbles larger than 7 Coumadin parsec, and they are also in overdense regions. And we found that bright galaxies have their because they sit in larger bubbles, so their lambda alpha transmission is much higher. Okay, thanks.
Thank you, Yuxiang. One question from Luke Barnes. How are you modeling the radiative transfer of Lyman alpha photons through the ISM and IGM?
Yeah, so it's a very good question. So we, in terms of modeling the ISM, because we are focusing mostly on the brightest galaxies, so the intrinsic line profile is not, we don't think it's very important to this study. And to modeling the IGM, we are not doing a full radiative transfer simulation. We couple our semi-NM model of galaxy formation with a semi-numerical code to do the neutral hydrogen fraction calculation in the IGM. So the code is called 21 centimeter fast, which has been shown by the previous speaker at the beginning of his talk. So this is a accurate a fairly accurate code to calculate the AGM neutral hydrogen fraction, but very fast compared to a traditional radiative transfer calculation.
Thanks, Yuxiang. Can you stop sharing your screen, please?
Yes.
All right, and we next have Anshu Gupta. And she'll be telling us about Mosul. So let's try this.
Let's move this here.
Move the screen.
I guess people can see me on Zoom as well. Right. Thank you. Thank you, Ivy. And this works great. All right. Hi, I'm Anshu Gupta. I'm Astro 3D Fellow at Curtin University. And I stand here between you and your lunch or afternoon tea. So I'll try to be quick. So as Ivy said, I'll be talking about the Mosul survey, where we are looking at epoch of reionization analogs at redshift 3 to 4 to sort of understand what's happening at this epoch. So to go back to what this epoch is, this is the brief history of our universe. It only spans about 13.8 billion years, which is very short. It's not. Yeah, so in this 13.8 billion years, universe started from this big bang where it was ionized. Then we went through the dark ages where most of the material was almost neutral. And after the dark ages, as the dark ages ended, they ended because the first galaxies and the first stars, they started forming. And these first stars and the first galaxies, they started creating these bubbles of ionized gas around and creating bubbles of ionized gas in this neutral intergalactic medium. And over time, as these bubbles, they grew, they overlapped, and they changed the entire universe from completely neutral to totally ionized around this, in only like less than 1 billion years. Okay, so there are two key properties of galaxies that drove this reionization. One is how many ionizing photons does these galaxies produce, right? The ionizing photons are basically the photons that can ionize the neutral hydrogen. And second key property is how many of these ionizing photons can escape the interstellar medium of the galaxy and go on to ionize the intergalactic medium, right? So in the next 4 or 5 years, JWST is going to really change or really put strong constraints on this production efficiency of ionizing radiations, because, all right, yeah, sure. Because there are a bunch of surveys that are really targeting redshift greater than 6 galaxies, and we are really going to get detailed analysis on the O3, O3H beta, N2H alpha, typical emission lines that are used to estimate this quantity. But even with GWST, we cannot measure the escape fraction of ionizing radiation because it will be blocked by this neutral intergalactic medium, right? So what do? What we are doing here is we look at galaxies that are way into that exist when the universe was totally ionized or mostly ionized, so that the escape fraction or the ionizing photons, they are not blocked by this neutral intergalactic medium. And we study their detailed properties and then plug them back into our models of reionization and see what happens. So for this, we are looking at data from our Mosul survey, which is basically an emission line, which is basically a survey of around redshift 3 to 4 galaxies, where we are targeting a bunch of emission line galaxies around redshift 3 to 4. And we have a really nice website, so if you are interested, go have a look. And we have a nice logo with a wine glass to make it look pretty. Right. But over the past 1 year, we have shifted the focus of this Mosul survey to really go after the epoch of reionization analog galaxies. And how do we do that? How do we select epoch of reionization analog? To do that, we are choosing this key property. Okay. To do that, we are choosing this key property of galaxy, property that we know of that exists for almost all redshift greater than 6 galaxies. That is, they have really bright emission line. So if we look at their photometric bands, we see that they have really bright emission in wavelength region where most of these nebular emission lines like O3H beta or N2H alpha fall. So much so that almost all of the flux in these bands is coming from this nebular emission line. For example, for this system, the O3 H beta equivalent width is about 1000 angstrom. That is, all of these redshift greater than 6 galaxies, they have really bright emission lines. So we can use this property to identify galaxies at lower redshift in the same way. And we do that, and we select a bunch of galaxies with extreme emission features at redshift 3 to 4. And for this, we use really extensive, about 40 photometric band photometry from the Z4 survey. And we have a sample of about 100 extreme emission line galaxies with O3 equivalent, with photometric O3 with equivalent with greater than 600 angstrom, and which makes them very similar to the O3 equivalent width of the observed galaxies. And this is one analysis that was done by Jonathan Cohen, and he used this extensive photometry to reconstruct the star formation of these extreme emission line galaxies. And what he found that these extreme emission line galaxies, they are undergoing a burst of their star formation. So this plot here, it shows the star formation rate in the past 50 million years on the x-axis, and the 50 million years before that on the y-axis. For typical star-forming galaxies, which is blue histogram here, the star formation history right now is very similar to star formation 50 million years before right now, right? It doesn't change much. But for this extreme emission line emitters, they are forming most of their stars in the 50 million years right now. That is, they are undergoing this peak in their star formation. That's the first burst of their star formation, and which is okay, because these are mostly low stellar mass galaxies and galaxies with bright emission lines. So we should expect that. But it's good to see that we can recover this behavior through photometry. So what's the next step? So the next step is we put a spectrograph on this galaxy and try to see what their spectrum looks like. Can we confirm our photometric selection? And yes, we do. We can, because we targeted about 19 of these galaxies with CMOS spectrograph on VLT, and we got a really beautiful emission line spectrum for almost 14 of these galaxies, which they had really bright O3 emission features. So this is like the nice emission spectrum from CMOS, and for some of the galaxies we even detect H beta. And the plot here, it shows the O3 equivalent width of our sample on the y-axis as a function of stellar mass. And it shows that most of our galaxies, which are these golden stars, they have O3 equivalent width greater than about 800 angstrom. And few of them are even like 1000 and above. Like one is like 2700 angstrom, which is crazy. And this is very high compared to the typical star-forming galaxies at redshift O3. Typical star-forming galaxies, they have a O3 equivalent width of about 500 angstrom. So it basically shows that our selection works. It shows that we are selecting these bright O3 emitters from our photometric technique. Right. So what do? We have such good quality spectrum, and we do confirm that these are bright O3 emitters. So what do we go to with that? The thing that I'm now looking at is, does this bright O3 emitters, do they show any sign of outflows? And I'm going to quote Adam here, because he said that earlier in the morning, that outflows regulate star formation, or outflows regulate how galaxies grow, right? So outflows are really important to understand the overall growth of the galaxy. Typically, to understand or see any signatures of outflow, we fit a multi-component Gaussian, typically a 2-component Gaussian, and we see if there is a systematic signature of outflow. If we see an outflow gas that is systematically flowing away or from the main component of the galaxy, and if we find that, we can estimate overall mass in that outflowing gas. But the resolution or the signal to noise of our data is not sufficient to really fit do this multi-component Gaussian fit to the emission line. So what other thing can we do? What other thing we can do is we can use another non-parametric way of estimating or seeing if we see any evidence of outflow. And in this version, what I do is I calculate W80 parameter, which is basically the velocity bit that contains 80% of. Oh wow! Okay. I am going way slower than I should. Yeah, so I calculate W80 parameters, which is velocity width that contains 80% of the emission flux. Right, and for a typical Gaussian, it's about 1.1. So this is the W80 parameter that I get for most of my galaxy, and I can do this. I can only do this when I have really high signal to noise. Also, no sky contamination because this is non-parametric, right? And I'm comparing my results with another sample, which is around redshift 3 galaxies. These observations are done with Moth fire. But there the sample was selected to be typical star-forming galaxy, and as is evidence from this y-axis here, x-axis, which is O3 equivalent widths. So you can see that when we look at galaxies, which are these extreme emission line emitters, we are getting W80 parameter, which is significantly higher than the one we should expect. All right. One we should expect based on the Gaussian. Basically, what this analysis show is there may be some sign of outflows in these extreme emission line emitters, and what I can do is I do a simple calculation to see if I can recover the flux and the velocity within this W80 parameters, and we do see that almost all of these extreme emission line emitters, basically O3 galaxies with full width half maximum greater than 1000, they require at least 20% flux in the broad component to reproduce the observed W80 parameters. Right. And I'm going to stop here. I wanted to shout out one thing that today I got a really good news that I'll get X-shooter, like 2 hours of X-shooter time on 11 of these galaxies, which is going to be fantastic because we'll get rest UV to rest optical emission lines, hopefully for the brightest emitters in my sample. So that's going to be fun. Right. And also, please, there is this survey that we are doing as the ASACR chapter. So and it was shared on Wednesday. So if you can please share it with all of your contacts, it will be really good. We want to build as large a database as possible. So please share it with your contacts. Thank you. And I am sorry.
Thank you, Anshu. You didn't actually go over time. You just panicked at the 2-minute mark. So.
Oh, it was the 2 minute. I thought it was.
No, that was the, sorry, my bad. But there are 3 questions in the Slack. So Yuxiang could ask if you could please comment on the potential redshift evolution when using low Z analogs to study high Z galaxies.
Yeah, that's a good point. We do have to worry about the effects that we might not be selecting the exact mimics, right? There might be some differences in the analogs, but the analogs is our way of saying if we are selecting our analogs based on these 3 or 5 parameters, and this is the behavior that we get. And if our epoch of reionization galaxies were similar in that respect, then that's what we do. But there is that limitation that we might be missing something and we might be over exaggerating.
Okay, second questions from Sabina Belstedt. In the CON 2018 plot, it looks like the 0 to 50 mega years EEL GSFRs are quite discretized. Is there a good reason for that?
Which paper?
The CON 2018. So
maybe I'll answer it on slide.
Yeah, maybe answer it offline. And then there's one, oh, congratulations on the X-shooter time allocation from Thomas Nordlander. Adam Stevens asked, is the results that the EELG having boosted star formation an inevitable result of how the SED fitting is done?
No, I don't think so. Because we do see that even in their UV and near infrared bands, we do see excess in the Spitzer. So that might also show we do see excess in the IRAC band. So that does show that they have higher star formation rates.
Cool. And do we have any questions on Zoomland or local hubs? Nope. If not, let's give Anshu and the rest of the speakers a hand for the fantastic science and also for taking the time. Right, have a good break. Cheers. Bye.